Hello, ladies and gentlemen. I am Xiaozhi from Shanghai Jiao University. It is an honor for me to present our work, SpaceExit, enabling efficient adaptive computing in space with early exits. I will introduce it in these 4 parts. Let's start with background and motivation. Let's start with the big picture. Earth observation constellations are no longer a niche technology. They have become critical global platforms. They support a vast array of high-impact applications, from enabling precision agriculture, providing crucial data for disaster response, to performing large-scale environmental monitoring and optimizing transportation logistics. This explosion in capability is supported by rapid technological advancements, particularly in the iteration of nanosatellites and the decreasing cost and the increasing frequency of rocket launches. However, this growth creates a problem. The traditional method for handling satellite data is the bandpath architecture. In this model, the satellite acts as a simple relay. It captures data and pipes it all down to the ground for processing and inference. The fundamental issue is the imbalanced growth between the data being collected and the bandwidth available to transmit it. If we look at the last few decades, the trend is clear. On the first graph, you can see the satellite resolution, a proxy for data volume, has improved exponentially from kilometers in the 70s to well under a meter today. But on the second graph, you see that channel capacity, or downlink bandwidth, has grown at a much slower pace. We are collecting data far faster than we can send it down. This is the bottleneck that bandpipe architectures can no longer handle efficiently. A promising solution to this bottleneck is orbital edge computing, or OEC. Instead of sending raw data, OEC performs inference on the satellite and sends down only the much smaller results. By adding a computing layer on the satellite itself, we process data where it is collected. This dramatically reduces the strain on the downlink. To put our work in context, it's helpful to see how researchers have traditionally tackled the satellite downlink problem. Efforts have generally fallen into 3 categories. The first is transmission coding. The main goal here is to make the data signal itself more robust and efficient for the unique and challenging satellite-to-ground communication channel. The second major area of research is image compression. This is a more intuitive approach. If the data is smaller, it's easier to send. A lot of work has gone into making image and video files take up less space. So, while advances in transmission coding and image compression have certainly helped, they have not fully bridged the fundamental gap between the explosive growth in data volume and the slow growth in bandwidth. This is precisely why more researchers are turning to a new paradigm, orbital edge computing. On this slide, we see two important recent systems that embrace this philosophy: Cordon and target fields. Cordon leverages specialized machine learning model selected based on prior knowledge about observation targets. This approach improves efficiency through targeted processing while dependent on the accuracy of prior information. Target fields employs a combination of adaptive tuning, object clustering, and bandwidth-aware transmission scheduling to minimize detection errors under resource constraints. This hybrid approach balances onboard processing with efficient data transmission. But satellites in orbit encounter a constantly changing environment and workload. Satellites face severe thermal variations moving between sunlight and Earth's shadow. Satellite-to-ground communication bandwidth varies dramatically based on orbital position and ground station visibility. And most importantly, continuous Earth monitoring generates spatial and temporally correlated image sequences with varying complexity. A satellite might be looking at a simple uniform expanses of ocean 1 minute and a complex dense urban city in the next. An existing approach to handle this is multimodal system, which tries to select an appropriate predefined model based on geospatial context. However, this static approach has significant drawbacks. Predefined rule for foreseen classification or object detection may fail when confronted with unexpected phenomena or rapid changing environments. And the extended time spent loading different models will significantly impact system efficiency and responsiveness. Therefore, we adopt an adaptive processing pipeline that adaptively modulates computational intensity based on real-time scene complexity and resource. It can achieve superior efficiency by enabling early termination for simpler inputs while maintaining high-fidelity processing for challenging scenarios. While implementing a truly adaptive method for Earth observation processing holds great potential, implementing such a system presents several significant challenges. First, satellite imagery requires the processing of multi-scale image information and incorporation of geospatial context, which is not typically considered in the traditional method. Second, adaptive approaches must continuously adjust the resource allocation based on current input and system state, challenging in satellites with multiple heterogeneous computing devices. Third, the ever-changing space environment and varying mission requirements pose unique difficulties in runtime management. So, we need an algorithm system co-design to tackle these challenges. And that leads to the next part. I would like to introduce our holistic system design. We deal with the mentioned challenges through algorithm system co-designs of SpaceExit. I'll briefly overview them now, with details following in subsequent slides. Complexity-driven adaptive task scheduler module schedule tasks for heterogeneous devices. Geospatial-contextual adaptive detector module process satellite imagery with varying complexity. And the satellite resource adaptive controller module manage runtime resource under onboard constraints. Let's start from the complexity-driven adaptive task scheduler module. It first uses a difficulty assessment model that estimates the processing complexity (dt) of each image. This model can leverage simple heuristics or train a simple low-complexity model. Then, tail sizes vary based on difficulty scores. This approach is motivated by the observation that satellite images often obtain regions of varying complexity, and uniform tailing can lead to inefficient resource utilization. These tails are then allocated across available onboard devices, considering factors such as tail complexity, device capabilities, and the current workload. For each device I, scheduling submodule maintains a FIFO-QI. The scheduling process for each tail R involves assigning it to a device queue. The device selection policy below the device selection policy below aims to equalize processing time across devices while avoiding the queue overflow. This adaptive approach ensures efficient load balancing and maximizes overall system throughput. Secondly, to balance detection accuracy and computational efficiency across diverse satellite imagery, we propose a geospatial-contextual adaptive detector module. It employs a multi-scale feature backbone with multiple exit points, allowing for adaptive adjustments for processing complexity based on image content. This backbone is designed to capture features at various scales, which is essential for detecting both large-scale structure and small details in satellite images. After each processing stage, the router will be activated to judge whether the model should process to the next block or go to the head to get the prediction and exits. This adaptive routing allows GCAD module to allocate computational resource efficiently, dedicating more processing power to complex images while quickly handling simpler ones. What's more, we trained a lightweight threshold agent to help to select the most appropriate scale and exit point for each image tail, leveraging both semantic context and geospatial context. Finally, the satellite resource adaptive controller is designed to maintain safe and efficient system operation under the dynamic constraints of the space environment. One of its functions is to adaptively allocate energy resources among onboard computing devices in order to maximize overall system throughput. The allocation policy operates in two stages. First, it reserves a base power P-base for critical satellite systems, then allocates remaining power among computing devices based on their performance sensitivity to power. Thermal management is also a critical aspect of its RAC module. It continuously monitors chip temperatures and proactively adjusts power states when temperature approaches the limits. This allows for smooth throttling of DVFS settings to maintain safe operation without abrupt shutdowns. Its RAC can also adjust the processing threshold used in the GCAD module based on current resource availability, allowing the system to be more conservative when resources are constrained, and more thorough when resources are plentiful. The following figure clarifies how SpaceExit works. Input images will first be partitioned into tails and assigned to different devices. While devices process computational tails, the SRAC module monitors runtime states across all devices and dynamically allocates resources. GCAD module takes the assigned tails and outputs the detection results. Changes in device state induced by resource allocation and tail processing propagate back to the scheduling subsystem. Then, I would like to introduce the evaluation of SpaceExit. To prove the effectiveness of SpaceExit, we conducted a thorough evaluation. We used the widely recognized satellite dataset for object detection. We compared our system against 4 strong baselines: traditional bandpipe, a naive space-only approach, and 2 state-of-art systems, cordon and target fields. We tested across multiple hardware configurations, combining NVIDIA Jetson NX and Nano boards, and under different simulated bandwidth conditions. Our first key result is on good puts. The amount of useful, correctly processed data delivered. The chart shows the normalized throughput for different hardware and bandwidth sets. In every single configuration, SpaceExit, shown in red, significantly outperforms our baselines. We measured an improvement of 5.2% to 37.6%. This is a substantial gain, meaning more valuable insights are delivered from orbit. We also measured the mean average precision, or MAP. This table compares our adaptive GCAD with a stacked model. Not only does SpaceExit avoid accuracy degradation, it actually provides a slight improvement in MAP. This shows our adaptive approach is more efficient and highly accurate. Finally, I would like to show the conclusion of our work. To conclude, we have presented SpaceExit, an integrated system that enables efficient and adaptive Earth observation on satellite through a deep algorithm system co-design. It directly tackles the key challenges of OEC: handling multi-scale geospatial data, scheduling across diverse devices, and managing dynamic onboard power and thermal constraints. Our evaluation shows that it significantly outperforms existing methods in practical metrics like good puts, without compromising accuracy. Ultimately, SpaceExit enhances the data delivery capacity of satellite constellations, strengthening their roles as powerful platforms for a wide range of applications. Thank you for your listening. If you have any questions about our work, feel free to contact us through email.